Hello,
Hi, Muskan.
how are you?
I'm good. How are you?
Pretty good.
So that's going to be a new topic for today, and
Yep.
that's chirality. So where does this word chirality originate from? So it's actually originating, or it's derived from the Greek word, which actually stands for hand. Okay,
Right.
and yes. So we spoke about mirror images the other day.
Yes.
So an object is said to be a chiral if the object and its mirror image are non-superimposable. Like, for example, if you take your left and right hand, okay. So what we must be wondering here is, I mean, when you say non-superimposable. So when the mirror image of the object is placed over the original object, they do not overlap. Understood?
All right. Yep.
So for example, if I take the right hand and the left hand, I put it this way, it's not overlapping. Okay. So you can say that the object and the image are said to be non-superimposable. Okay.
Mm-hmm.
Like for example, if you have a hand which is basically in this structure, okay, and the image with the thumb this side, okay, and the other fingers this side, okay. So if you actually, I mean, put them one over the other, they are non-superimposable. Now, same thing if I take a bottle and then take the image of the bottle, the image also will be absolutely the same one. Now, if I drag this over this one, okay, so what happens here is even the superimposed image looks like one.
Okay.
Okay, so then that is what we call it as a chiral objects. Okay, so chiral is this. When they overlap, you can't superimpose them. A chiral is when you actually can superimpose the images. So now what has this got to do with chemistry? Okay, so way back, you must have heard the name Louis Pasteur.
Yes.
Yes. So he successfully separated two isomers of sodium ammonium tartrate. Okay.
Okay.
And he observed that these two isomer crystals were non superimposable mirror images of each other. So when they were non superimposable, they had similar properties, but they differed in the ability to rotate in a plane. Okay. So that's basically an optical activity. Understand? So, for example, in non polarized light, electric and magnetic fields randomly orient in all the planes. Okay. You visually cannot see all this, but yes, that is what this happens actually. So, chiral molecules, they're optically very active, which means that a beam of plain polarized light passes through a chiral molecule. It interacts and makes that molecule to rotate on its axis. Understood? We have seen that axial symmetry, where the
Yes.
structure or moves or runs on the axis. So that's one example. Okay. So now the question here is, what are these chiral compounds and how can we actually identify them? So first of all, let's see what are the different chiral compounds that actually can they be classified into. First one, drugs. I mean to say medicines. Okay, pharmaceuticals. Then of course, sugars. These are all chiral examples, okay? So sugars are many, okay?
Yeah.
Can you name them?
White sugar.
No.
Oh,
I mean, you're not going to go by the color of the sugar. You're going to go by the structures. They are named differently.
isn't it like we did it in bio? It was like,
Yes.
I don't know, it's not, it's like glucose is
Yeah, glucose is one form of sugar. Good. Can you give me another form? There is sugar in milk as well. Come on, that's pretty easy to
lac
answer.
lactate,
Lactose.
lactose, lactose.
Lactose is one. There is dextrose. There is sucrose in sugarcane. You must have heard about sugarcane.
Yes, yes.
Yes. Then we have galactose. Then we have cellulose, which is found in cloth. And there is
In what?
fructose, cloth, CLOTH.
Like
But
blood
there,
clots?
there is no percentage of sweetness in it. 0% sweetness. Okay. Understood.
Okay.
And the most sweetest of all the sugars is fructose. Okay. What is it called as? Fructose.
Fructose. So like with an
F
F?
R S F R U C T O S E.
So how does it have anything to do with chirals or whatever?
But there are forms of sugars actually. I mean, sugars also can be classified under chirals. Now here we have to see whether do they possess these what do you say optical sort of a vision images or not. Okay, that's one which can be classified under chiral structures. Then of course we have amino acids which forms the base of the proteins. Then of course we have DNAs which also can be characterized under chirals, and then of course we have
What
enzymes.
about RNAs?
Not RNAs. RNAs are different, DNAs are different. DNA
No,
is
but would they
basically
not be characterized under that?
under what?
Under like this list of
No, because their
chirals?
structures do not, cater to this chirals. Understood? That's the
Uh,
reason. Yes, you can't.
okay.
So, the next question here is, how do we identify the chiral carbon centers? Okay. So here, what we need to understand basically is the chiral carbon centers are nothing but carbon atoms that are attached to four different substituents. Understand? In the center, you have the carbon. Okay, and then this one carbon is attached to four different substituents, so it forms basically a tetrahedral structure. Okay,
Okay.
so that's the reason chiral carbon atoms are also referred to as stereogenic carbons or asymmetrical carbon atoms. Like for
Yeah.
example, I'll just draw one and show you. I have carbon here. Okay, so these are my four tetrahedral arrangements. Here I have W. There, no.
Would the like the middle atom be like for the carbon? Would that be like the
Yes.
DNA, amino acid, whatever we're looking
Yes.
at?
So now, if I actually place a mirror, so the structure, I mean, you can see the image. If this is a mirror, then it will be somewhat like this.
So it's just the exact same. No, it's not.
Yes. I mean,
Wait.
it is, of course, the same thing. I actually messed it up here. This actually will go cross. So you basically
Okay.
will have the same, I mean, sort of an image. So here, what we can notice is the center in the chiral structure is the carbon, which is actually attached to four different substituents or four different groups, W, X, Y, Z. So
Yeah.
what can be said here is compound 1 has a chiral carbon center. Okay, so which is the chiral carbon center here? This one. So this I'm going to call it as 1. Okay,
Yeah.
so this is the first one. Then of course we have the next one. So if you look at the image, if this is my first one. The image here is the second one. Okay. Now, compound 2 is a mirror image of the first compound.
Okay.
Okay. Now, according to the definition of chirality, compounds 1 and 2 should be non-superimposable. They cannot overlap each other. Okay.
Yeah.
So then how do we confirm this now? So if you rotate compound 1 around one axis of rotation and see if any of the products of rotation leads to compound 2. I mean, if I rotate the first one, can at some point I get the structure of the image that was formed in the second one? Is there a possibility?
Yes.
Yes, at some point you will get this. Now see, y is on the right side, isn't it, in the first one?
Yes.
Now if I rotate it, so is there a possibility where y goes on the left side and w comes on the right side?
Yes.
Yes, it is a possibility. There is a possibility. So what it's saying here is
They're
if you
just
go
gonna be
ahead,
opposites. That's it.
yes, yes. So if we actually sequentially rotate the compound first, I mean the first one, about the cx axis in a clockwise direction, then of course what you can see is no. But will it
No.
form? Will it form? No, it will not. Because how will it form? Tell me.
What are we looking for? Just for it to like form?
No, w x y z, isn't it? Because
Yeah.
what happens in the first one is no x, w, z, and y. Even if I rotate it, y goes that side, w comes this side. No, there is no way that it's going to form. No, no, no. It can't superimpose. No way. Because I'll tell you why.
So it doesn't
No,
form.
no, no, yeah, I'll tell you why. Because I just need to redraw this again.
Okay.
I'll draw the exact structure how it actually should look like. Then we can conclude if it really superimposes or not. Let me get the exact structure. So with carbon at the center, okay, and then of course I have Z here. Okay, I got this. Here's the mirror, and then
I still don't get those like lines. Like some are dotted, some are fat,
no,
some are
one is
straight.
dotted because that is the axis of rotation.
Okay.
Yes. Now, even if I rotate this and bring the first one, okay, if I rotate the first one in a clockwise direction,
Yeah.
or even if I rotate it, what is going to happen here is, as you can see, this is why you will not have a structure that is actually going to overlap upon one another. It's not possible.
Okay.
Okay, because you see here I have y and here I have w. So even if I rotate this to the other side, okay, y and y will not overlap over one another, and therefore what's going to happen here is this is actually going to end up as what is saying, what I'm trying to say here is none of the structures when you rotate it is going to form the structure same as the mirror image, which is compound 2. So what we can say here is when it is not superimposing, then I'm going to call the first compound as a chiral.
Okay.
Understood? So that's one way of identifying it. Understood? Well, that's one
So when you're
example.
rotating and if it's not at the
It's
same
not
spot.
superimposable. Yes, if it is not superimposable, then we're going to call it a spiral.
What do you mean by superimposable?
When it is one over the other.
Okay, when it's one over the other. Wait,
Yeah.
why would it be one over the other? That's not possible, is it?
No, if it is possible, then it's going to be a chiral structure.
How would it look like if one's
Like for
over
example, if I have a T, so let's take a T here. The image of T also is going to be the same.
Yes.
Now, if I drag this T onto this one, can you tell me which is compound one, which is in compound two here in this?
No.
If this comes and overlaps over this, you can't say, isn't it?
Yeah.
Yes. So that's
So
what
it's the
that's called as
same thing
non
over
super.
there. If they
Yes.
can put them together like the T, then that
Exactly.
means they're not a
Exactly.
chiral.
Exactly. Exactly.
So
Okay.
if you can't put them together
Yes.
and they're not identical, then they are a chiral or whatever it
Yeah.
is.
Yes. Now
Okay,
suppose.
got it.
Okay. Here is one hand. Okay, with the thumb over here, and here I have another one with the thumb over here on this side. Now, when I superimpose this, when I place it over this, I'm going to see a thumb on this side as well, on the left side as well.
Yes.
Okay, see there. These are my two hands. I mean, two palms. Okay,
Yeah.
right. Now, if I superimpose them, see there. They are not
You see
superimposing.
thumbs on both sides.
Yeah, exactly. So it's not the same image that's forming when it's superimposed. This is a chiral structure. Now, something like this, suppose, for example, if two structures are this way, and I now superimpose, did they get superimposed?
Yes.
This is an achiral structure.
It isn't a chiral structure because they are
Now it is. Now, this isn't a achiral structure.
okay. The other one
Okay.
is.
Yes, the other one is.
Okay.
Okay. Yeah. So, understood this point?
Yes.
Yeah. So, next one, the next topic that we're going to discuss is enantiomers. Where is my white screen?
I think I've heard that before somewhere.
We discussed it the other day.
Oh, okay, then that makes sense on where I've heard it from. Also, we went through the properties of like, you know, alkanes, alkynes, and alkenes.
When? Today in college?
No, last week Friday.
Those are not properties of alkenes and alkenes. No.
Yeah, there is like low
No, no,
density.
that was for stereoisomers.
Yes,
We studied the properties of stereoisomers.
yes, of alkanes, alkynes, and alkenes.
Yes.
What's the difference? It's still the same. Well, no, I didn't say that.
No, no, no. It is not alkanes,
I did
alkenes,
not
and
say that.
alkynes. No, no, no.
No, but the slideshow, it was saying like properties of alkanes and then properties of alkynes and then properties of alkenes. And then, we
Okay.
were doing the hydrophobic, no color, highly volatile. Also, can
Yes,
you
yes,
explain
yes,
the
yes.
volatile? I just don't understand what that means.
I mean, you mean to say the
And
word
torsional
volatile?
strains,
You mean to say the word volatile? Is the
volatile,
meaning
yes,
of?
that one.
I mean, basically, what's the meaning of volatile in chemistry? You mean to say
Yes.
that? What, can you make a guess? What exactly is volatile? Okay, fine.
Melting and boiling point.
No, no, no. Volatile is basically a tendency of a substance to get vaporized.
Oh,
That means
okay.
a substance which has the capability or capacity to go into the vapor phase. Okay. And a substance going into the vapor phase, it has to be during heating or without heating as well. Okay. So
Oh, okay.
volatility and vapor pressure of a substance are both related. They are correlated. Now, if I say if the volatility of a substance is high, then the vapor pressure also must be high, isn't it?
Yes.
Absolutely, because volatility is nothing but tendency of a substance to go into vaporized state. So when it
Yeah.
is going into a very high vaporized state, That means the vapor pressure also must be high. Understand? So that actually relates to volatility. Like for example, if I drop alcohol, a drop of alcohol, after a while you'll not be able to see that. Why?
Yes.
Because it's it has a high tendency of going into a vapor state. Even gasoline for that reason.
Alcohol, like vodka and stuff, or like pure alcohol?
Pure alcohol. Do you have a
Oh,
sanitizer
yes.
handy?
Yes.
Put a drop of it on your hand. Rub your palms against each.
Oh, it's going.
That's it. So even sanitizer are highly volatile because it contains
I always thought it just moisturizes into your skin.
no. Do you know what it contains?
Alcohol.
Yes, and it is highly inflammable. Careful.
That I knew that.
It can catch fire. So okay, so it's
All
very
sanitizers?
yes, it's very crazy stuff actually. Okay, most of them do not know that, but it is very highly inflamed.
We've never
It's
been told that.
yeah, it is alcohol, so obviously it has to catch fire. Okay,
Yeah, true.
even in fact, all your hydrocarbons, especially deo sprays, okay,
Oh, dude, those
mosquito
are very flammable.
very because they are all alcohol based.
Yeah.
Okay, and they do catch fire very quickly. They're highly inflammable. Okay,
Hmm.
so coming to enantiomers. So a chiral compound and its mirror image are referred to as an antiomer. I mean enantiomer.
Okay.
Okay, try to understand the chiral compound and its mirror image. So what you can say here is an enantiomer is being two stereoisomers that contain asymmetric carbon atoms, which are non-superimposable mirror images. They cannot superimpose themselves because see, the moment I use the word chiral, so the first thing that should strike your mind is okay, if they are saying it is chiral, so they cannot superimpose over each other. Okay, so enantiomers, they differ only in their optical activity. I mean, the direction in which these actually rotate in a plane polarized light. Okay,
Okay.
so for example, if an enantiomer rotates the polarized light to the right side or in a clockwise direction, it is said to be positive. Understood?
Yeah.
Anything that goes in the clockwise direction is positive. And the same thing, if it goes in an anti-clockwise or a counterclockwise direction, then that stereoisomer is called a negative one. So what can I call this positive isomer here? It is called as dextrorotatory isomer.
Should I know this? Like what then like
Yes.
what would they ask on a question? Like draw an antiomer or like a
They might
chiral?
ask you
What would a question even be for like stuff like this?
clockwise. No, it's up to them. Okay. Because you also have it in your portions syllabus saying that there's going to be a huge long discussion on this, and especially you need to identify them. It's clearly mentioned. Okay. And
Identify like antiomers and like
yes,
they're
yes,
probably
yes.
just gonna ask every single time they've always asked like how to like relate it to a real life scenario, how it can be used in like to upgrade medicines or something like that.
Absolutely, yes. We'll come to that point as well. Okay. So what we have seen is a positive, and enantiomer that rotates the polarized light in a clockwise direction. Then we call it as dextrorotatory isomer. The same thing, if it rotates in a counterclockwise direction, then we call that as levorotatory isomer. Levorotatory.
Anti-clockwise is the opposite way a clock goes, right?
Exactly, exactly. Those are called as
Yeah.
anti-clockwise. Okay. Now these enantiomers also have the same physical properties. Okay, except for the direction in which they rotate the plane polarized light. Okay, so here these isomers exhibit different optical activities. Okay, and they
Yeah.
are also sometimes referred to as optical isomers. So there are multiple names given to that actually. Okay, And after this is the most important thing. I think you have it in your curriculum as well. Assigning R and S configuration to chiral centers, because there is, you have to configure each chiral carbon of two enantiomers, okay, which is systematically assigned using the R and S system. This might sound,
R and S.
yes, which is called as the
Hmm.
R and S system.
Is this like another step to like add or just
Yes. So actually,
onto antiomers or like every single thing out
no,
there?
no, this is actually a method of naming the enantiomers, which was developed by three chemists. The first one, this guy's name was R.S. Khan, not Khan, Khan. You can also call it as Khan, C-A-H-N. Then
I thought he was a Pakistani.
yes, C. Ingold and V. Prelog. So these were the three chemists who actually, enunciated certain rules of naming the enantiomers. So Khan, Ingold, Prelog rules is what they call. Now, what I'm saying here is, if I talk about an stereoisomer, which is an R group, so it can either be a positive one or a negative one. You know how to name it positive and negative based on in which direction are they rotating,
Yes.
clockwise or anti-clockwise. Okay.
Wait, how am I gonna know which direction they're going again?
Yes, there is a method for it. We'll come to that.
Oh,
Okay.
is this the RNS
Mm,
system?
yeah,
Yeah.
exactly. And then optical activity of RNS stereomers have to be measured experimentally with a specified meter, which is called as the polarimeter. So now here we are going to first notice how can we assign this R and S configuration to the chiral centers. Okay,
Okay.
we shall see that first. So let's take
So
carbon. Yes,
the Cairo thing is technically just them going if they can go. What's that word?
clockwise.
No, that would be the antiomers to know if they're going anti-clockwise or clockwise, and to know if they're
Yes.
the D word or the other word.
Yes.
And then so that means the
Dextro
chiral would be
rotatory
like
and
this.
levo rotatory is what you're saying.
Yes. So that is just antiomers, but then the Cairo would have been like if they overlap each other correctly or
Yes.
not.
Yes.
Oh my God. Okay.
So
So
this
they're
is
all just little things with big fat words which just make them sound really confusing.
so
Okay.
here is a chiral image, not image. This is the original structure. We have a Y, X, W, and Z. Okay, so this is how it looks like. Now, this is going to get characterized into three different, what I can say, divisions. Okay, the first one is called as a solid line, and that
Yeah.
is this one. Now I'll use a pink color here. This whole thing is going to be called as
Solid line.
this part of the chiral is what we're going to call it as solid line.
Yeah.
Okay. And what about this one then?
Isn't that the dotted line, the blue one for Z?
No, we'll go to this first. What about this? This, I'm going to call it as a solid wedge. The meaning of wedge, what generally wedge means in English,
Yeah.
WEDG, what is it?
It's like a really thick thing, but it's a
Oh,
bit weird to describe, but like
exactly.
I could probably
Yes.
draw it.
Like one thick and one thin pointed end. Okay.
Yeah. It's like a triangle, just
Yes.
3D.
Yes. And then, of course, we have the third part, which I'm going to use this color, which is a brown one. Now, the one which I drew in blue color, the line, it's actually not a line. Okay, because
That's the
it's
dotted
actually
one.
no, it's actually yes. I mean, I can call it as hashed. Okay,
Does that mean W was supposed to be the wedge? Like the thick one?
yes, yes.
Okay. Mm.
So this basically is hashed wedge. So a chiral is basically been divided into three groups here. Okay. So
And is
first
it
of all,
always going to be like this?
yes, 99%. Okay. So here, what's a chiral? Four groups attached to a chiral carbon atom. Okay, which is arranged in the relative order of priority. Okay. So what is saying here is the group with the highest atomic number is given the highest priority, and the group with the lowest atomic number is given the lowest priority. For
Mhm.
example, okay, instead of assigning just words here, if I actually, uh, give names, just not one sec, or the same thing. If I give names to it, okay, why did I draw the fourth one again with a, this actually has to be a hashed wedge. Okay, so the first one, here it is bromine, then here we have a chlorine, and then the two other ones are fluorine and hydrogen. Okay, now what they've done here is they've started numbering from here 1, 2, 3, and 4.
So
Now,
you'll always
yes,
number them
now,
anti-clockwise as
yes,
well?
yes. So why did I do that? Now, if I look at bromine, I'm going from the highest to the lowest. Okay, so
Yeah.
bromine has the highest atomic number, so its priority number should be 1
Okay.
because its atomic number is 35.
Oh,
Chlorine is 17, fluorine is 9, and hydrogen is 1. So basically, I'm going in a descending order.
okay.
Okay. Now tell me, did I move in the opposite, I mean, clockwise or anti-clockwise direction?
Anti-clockwise?
Exactly. So here, if I start from hydrogen, it's pointing towards this side now, isn't it? 4. 1,
Yes.
2, 3, 4. We are moving in an anti-clockwise direction. Now tell me, what kind of a chiral is this?
That would be something starting with an L.
Yes, levorotatory.
Levorotatory.
Okay. What
Yes.
is it? Levorotatory isomer.
Levorotatory
Rotatory
isomer.
isomer. Exactly.
If I know
Okay.
how to spell it, that'll be fine. If I don't know how to say it, it's fine.
It's very easy. You know rotatory, right?
Yes.
So add a lever to that.
Okay.
Levorotatory. So
And then,
basically, now you understood how are we moving?
so it's just going from the lowest atomic number, highest atomic number to the lowest.
Yes. Now suppose if I interchange something here. Okay. Wait, let me draw another structure.
No, but what if there's like a really high like atomic number between like
No,
fluorine and
they
hydrogen?
they'll oh, but depends. Where is the highest from? Where are we starting? Now I'll give you an example of a similar one. See, I'm going to put bromine here. Okay. Then I'm going to put chlorine here. Okay. Then where do I put hydrogen? Here I'm going to put fluorine. And chalo, here comes hydrogen. Now tell me out of these four, which is the highest one? Bromine, of course.
Now it'll go clockwise.
30 exactly. Now it's going to go clockwise.
Clockwise.
Then here, then one. No matter what this numbers are going to be, but after bromine, I have chlorine, which is the highest one. So I'm going to move or rotate in the clockwise direction.
So after the first one, it doesn't matter where you're going.
Exactly.
So
Okay.
even if there's like in between like fluorine and hydrogen,
Doesn't
if
matter.
there's like I don't know, like a carbon or something,
Yes. Now carbon, of
it
course, will
won't
be in the
matter.
center. Yes.
Oh no, not carbon. Oopsies. Sulfur or something like that.
Yes. Yes.
It won't matter at all because you've already gotten the first two. Okay.
Yes.
Got it.
Okay. Is that understood?
Yep.
Yes. So well, that's what it's saying. How are we supposed to proceed if the lowest priority group is not pointing away from us? So
Okay.
then you will have to, or you need to select any one of the two groups that are present in the plane of the molecule that
Yeah.
rotates the molecule about the axis. Okay,
Yeah.
that's the one which I actually showed. So priority number is assigned to atoms that are attached directly to the stereogenic carbon. Okay, now
Yes.
for example, I think up to this point this is fine. Now, where exactly can chirality and drug development? I mean, how can chirality be used in drug development? Okay, because even today, I mean, the importance of chiral drugs in the drug development space cannot be understated. Okay, because
Why
this
does it matter if the atoms are like just moving? Or does that have something to do with like the isomers?
I didn't get you.
Because like you know how it's like going anti-clockwise and clockwise, right? Like with
Mm-hmm,
the
mm-hmm.
everything's going anti-clockwise and clockwise with the carbons. Why does it matter so much? Because the properties aren't getting changed like the isomers where like the
No,
chemical is
but
staying the
somewhere
same.
down the line, even if one of its property will be different, it still pulls out a big or huge difference in the end. Okay,
But
like
it would stay the same, wouldn't it?
no, the chemical connectivity might be the same. Okay, but
But
still,
the property will always
yeah,
stay the
yeah.
same because it's
No,
gonna
no, no, no,
continue
no,
going,
no.
right?
No, what happens here is, like for example, if I say that the enantiomers of chiral drugs have the same chemical connectivity of atoms, but still they exhibit a lot of differences in their pharmacology or toxicology or what do you say, pharmacokinetics or metabolism when you actually finally synthesize it. Okay, because what happens is when are you saying chiral when you have two images which are not superimposable. Okay, so then much of
But
the
would that be
effort,
like in
yes,
medication to find
yes,
two
exactly.
medications
So there
where
is much effort that goes towards the separation of these two enantiomers. Okay,
um
yes, and that's
so
why
they
he
want
says,
to try and remove like
yeah, there are again differences in it. Like for example, if I say the enantiomer of a drug will differ in their interaction with enzymes. Okay, the behavior towards enzymes will change. Behavior towards proteins are different. Okay,
yeah.
and these differences in interactions again can lead to differences in the biological activity of the enantiomer. Like I just now mentioned, yeah, when it comes to metabolism or toxicity of that particular drug, the immune response of it. Understood?
Yeah.
So, yes. And
Okay.
when you're talking about drugs, now we have the first enantiomer, we have a mirror plane on the other side, we have its image. So, one is active, the other is an inactive enantiomer. Okay. So that is how actually it works.
What do you mean by inactive? Like it's just not moving?
It's not move. I'm not saying it's not going to move, but their locations of these two substances are different. Just like my fingers, as I said. I mean, one is not going to overlap with one. One is going to overlap with the five. Okay, or the fifth one. I mean, if you see here, if I number my thumbs, one, two, three, four, five. Here, one, two, three, four, five. See, two is actually going to overlap with the fifth one. So the overlapping of or superimposing of these what do you say enantiomers are not the same. Understood? And that actually can create a lot of difference. Okay,
And is that like what
so
happens inside like the
yes,
pharmaceutical
yes.
drugs?
So when I say that it is inactive, okay, like the inactive enantiomer, because the contact here is insufficient. Because if I have like three substances A, B, C, okay, and B and C have changed their locations. Okay, I will just show it to you in this way. One sec. Go here. This is D.
So is this like an active ongoing thing inside like tablets
Yes,
itself?
exactly. So I
So if
have
I pulled
something.
up a tablet, that means there's probably an anti-clockwise and a clockwise thing going
Maybe
on.
yes, in its chemical structure,
Like
yes,
the atoms are just continuously moving inside it.
yes. Now, if you see this particular diagram, which I actually put up on the page, now you can see the sequence of ABC. Okay,
Mm-hmm.
the first one that's an active one on the left side, and the right side is an inactive one. So one sec. This is the active one. and this is the inactive one. So
Is it because it's not in the correct order?
yes. So the three substituents ABC of the active enantiomer can interact with three binding sites of a receptor by forming three contacts here. Okay.
Yeah.
But the three contacts should be like AA, BB, and CC.
Yeah.
But if it is inactive, it can't happen so. Okay.
Oh. So
So
it needs to
one,
be in the
yes.
corresponding order.
So in this case, what can happen? One enantiomer is biologically active while the other is not. Okay. And because, so what is trying to say here? I mean, the substituents of the active enantiomer, which is labeled A, B, and C, must interact with the corresponding regions of the binding sites, which is again labeled small a, small b, and small c, for example. And so here what happens is the alignment has to be perfectly done. Like, for example, let me again extend with this. This is a small a, this is a small b, and this is a small c. And excuse me, here also I have a, here I have a b, here I have a c. So if I look at this, this is AA combination, this is B and B combination, this is C and C combination. So if this has to interact with another enantiomer, it should be in the same sequence. But see
Yes.
here, I do not have the sequence here. This is a sequence absolutely different here. It is AA, BB, CC here in the active one. Here in the inactive one is CA, AB, and BC, which cannot
Yeah.
be correlating. They don't correlate at all.
Okay.
Understand? So in this case, the fitting interaction produces an active biological effect. But if the alignment is not going to be correct, then it is an inactive biological effect. Okay?
Okay.
So there's no active response if they're not same. Understood?
Okay.
Yes. So
And if there's an inactive response with the active, does that mean that can like cause some sort of like malfunction or something?
I mean, the drug will be actually of no use. Okay. Absolutely no
Oh.
use.